Okay, thanks a lot. Okay, so okay, so thanks a lot for the feedback in the feedback form to people who responded. So one comment which came up a lot is that people maybe are confused about this abstract linear algebra portion of the course, or maybe don't understand what the point of it is even. So let me just say a bit of that. So okay, so the high level, the point of abstraction is that if you have an abstract definition like the definition of vector space, you can handle many different kinds of objects at once. So now using the linear algebra, we can talk about polynomials, we can talk about functions, we can talk about vectors in Rn, because all of these have the same structure of a vector space. But really, the power is that we haven't just defined abstract vector spaces. What we have is we have a how to describe it? We have a chain of equivalences between abstract and concrete concepts. So let me demonstrate this by going through the solution of problem 9 of the midterm. So problem 9 of the midterm asked, is there a non-zero vector in R2 such that if you rotate it, or sorry, if you reflect it across the line that makes a 45-degree angle with the x-axis, or sorry, if you reflect it and if you rotate it by pi by 6 radians and then reflect it, is that the same as doing it in the opposite order? Okay, so now, so the point is that this is actually I don't really have an easy way of solving this question without linear algebra. This is a question in geometry. This is asking if these two geometric processes of rotation and reflection. So remember, so reflection is the thing which reflects something across this line. And rotation is a linear transformation which takes a vector and rotates it by pi by 6. And the solution of this problem was to turn it slowly into a very concrete problem, right? So the first step, which was to say that, well, you have standard matrices of these transformations. So the standard matrix of reflection is this. And the standard matrix of rotation by pi by 6 is this. And this is a mechanical process. You can, and the standard matrices have this important property that multiplying them is the same as composition, right? So the AB is the standard matrix of the composition T ref of T rotate. And so you go from this geometric question, you get to translate this into an algebraic question. That is there a non-zero vector V so that ABV equals BAV? And now, now you can do things of this that you couldn't do with the geometric question. For example, you can rearrange it. And now if you do this calculation, you get that AB minus BA is this matrix. Okay. And now you can just solve this using row reduction, right? Is there a matrix of -1, 1, 0, 0, V? Is there a vector V so this equals 0? And the answer is no by row reduction, right? And so the point is that you turn this abstract question in geometry into a question in algebra. And really, it's this whole chain of, it's this whole chain of equivalences that's useful. That's, I mean, you'll see more in the next week. So we're going to start the sort of really interesting part of the course next week. But this is one, I think, quite compelling example of why abstraction is useful. Because I actually don't know a good answer to this question without doing linear algebra. Any questions about this example? Okay. And another thing that came up a lot is that some people, I mean, this might be the first time that you are being forced to, you know, write down definitions very precisely. So let me say a bit about why that's so important. And I mean, to really emphasize why that's important, let me sort of contrast what we're doing with some other fields of knowledge in which, you know, which are interesting. So let's compare statements in politics, physics, and math. Okay. So here's an example of a statement in politics. The election was rigged. Okay. So that's a very interesting statement. It's obviously very important. But now, how do you tell if such a statement is true, and how do you convince another person that such a statement is true? I'm sure many of us have found true or false, you know, whatever, right? So how to verify, how to convince someone else? And if you've tried doing either of these things, you come up against the following difficulties. So one is that there's actually no consensus on how to verify such a statement, right? No consensus. Okay, so you could do many things. You could go try to get first-hand knowledge. But that's kind of impractical, right? This is something that involves a lot of people. It's not so clear if you can actually do that. Or you can decide to trust the news media, but then you have to decide which information sources to trust. Or you could decide to trust social media, et cetera, et cetera, et cetera. But the common thread in all of these is that you actually need, unless you go with this first-hand knowledge option, which is usually very hard or impossible, you have to trust some authority. I mean, this is what's, I guess, being called a trust deficit right now, which is causing a lot of problems. And part of the difficulty is that there's no consensus on how to verify. There's also no consensus on what the words exactly mean. Like there's actually no real consensus on what the word rigged means, right? Okay, so that's one extreme. That's obviously a very interesting area, but it's very hard to verify statements, and it's hard to convince other people, and it's very interesting. I mean, but then you can have a field like physics, where you have a statement like the speed of light is 300,000 meters per second, approximately. So here there is a consensus on how to verify. The consensus is that the method is experiments, right? So there's a scientific method. There's a generally agreed upon notion of what an experiment is, although it's not 100% agreed upon. There is controversy about experiments. But you know, there is a mechanism by which you can check if such a statement is true. But often, even if you don't conduct the experiment yourself, and you do end up trusting the scientific community, right? So so you need some trust in, you know, you still need to believe the scientific method, right? And if you want to convince another person, they need to buy into this system, right? They need to share this trust. And in math, you have very boring statements like, yes?
I think you're missing 3 zeros.
Sorry, kilometers per second. Thank you. Okay, so that's a false statement, but yeah, now it's approximately true. Thanks. And so in math, you have some very boring statements like if AB is invertible, then A and B are invertible if they're both square. So let's assume they're square. If A and B are square and AB is invertible, then both A and B are invertible. Okay, not all statements are so boring. Of course, you have very interesting statements in math as well. But the point is that so first of all, there is a consensus on how to verify. So to verify, all you have to do is check the proof yourself. And to check the proof yourself, you need to know the definitions, right? So just check proof line by line. And this is a mechanical procedure given the definitions. And moreover, you can convince anybody of this statement, right? So the method of verification in math is such that you can check the proof line by line yourself. And you can convince anyone of the truth of this statement, and they can be your enemy, right? Can convince anyone of the truth of this statement without any need for trust. They don't need to trust you to be convinced of this statement. And this only works because we have very precise definitions because we have precise definitions. But anyway, this is sort of another reason why it's important, because if we don't agree on the meanings of words, then we can't have a conversation with these properties. I find this to be a pretty interesting definition of math, actually, that math is the only field of knowledge where you can transfer belief in a statement between any two human beings without trust. So anyway, this is some very high level philosophizing, but any comments or questions about this? Okay, well, let's, okay, and I want to make a few comments about, so many people said in the feedback that they're having a hard time keeping up with lectures. So one comment is, well, okay, I'll try to slow down, but one comment is, don't write everything down, right? Because I do post the lecture notes. So only take notes selectively, only take selective notes, and mostly just try to listen, I guess, to what I'm saying. And I'm going to try and, so one other issue was that people aren't able to look back at the notes. So I'll try this new thing today where I'll post the notes on Dropbox midway. So at least you can scroll back to the first half of the lecture. Let's see how that works. And then a lot of people said that they're feeling lost in the course and frustrated. So, I mean, it's a really hard time especially during COVID, and so don't feel bad. I think a lot of people are feeling lost and frustrated. But one thing you could do to try to feel less lost is, please reach out to all these, all the resources that are available for support. So, if you're lost, come to my office hours. A lot of people said they can't figure out what they would need to improve to do better on the next midterm. I can help you with that. So please just come to office hours and talk to me or talk to the GSIs. Yeah, and I acknowledge that it's especially stressful this semester. It really is a hard time, so don't be hard on yourself. Okay, so given that, let's proceed with the lecture. Any more comments or questions? Okay. So so let me now briefly review what we did last time. Or last two times. So last time and the time before, we developed this correspondence principle, which was based on isomorphism. So if you have a vector space B and it has a basis, let's say B1 through Bn, then we saw that there's a way to, there's an isomorphism between V and Rn given by the coordinate mapping, and its inverse is this map PB. And this has the very important property that any statement that's true in V is true in Rn and vice versa. So any statement about vectors, such as this is true if and only if the corresponding statement is true about the coordinate vectors. Okay, and then in the last lecture, we extended this type of correspondence to linear transformation. So now suppose you have a linear transformation between two vector spaces, V and W. And now suppose they have some basis B, which has n elements, and W has a basis C, which has m elements. Then you can now, you can look at both of these coordinate mappings, right? Which are both isomorphisms. And you get isomorphisms with these spaces Rn and Rm. And then down here, there's a matrix, which was denoted T subscript B comma C, the matrix of T relative to the bases B and C. And this is an m by n matrix. And this has the property that T of x equals y above if and only if, when you apply this matrix to the coordinate vectors, the same thing happens downstairs. And using this, we were able to translate problems and theorems in abstract vector spaces to problems and theorems in these concrete vector spaces. So last time I gave an example of how to transfer, how to solve a problem, about bases for the kernel and range of a linear transformation by applying this correspondence on the right-hand side and turning it into statements about the null space and column space of a matrix. So this is a matrix, right? This is the matrix of T relative to the bases B and C. And so now what I'm going to do is I'm going to tell you, I'm just going to give an example of how to translate a theorem using this correspondence. Okay. So here's a theorem. So if T is a linear transformation between two vector spaces, and both of these have finite dimension, then the following two things are true. If T is onto, then the dimension of V has to be at least the dimension of W. And if T is 1-to-1, then the dimension of V is at most the dimension of W. So this may look familiar because we proved a theorem like this about matrices. But now I'm going to prove the theorem about any linear transformation using this correspondence on the previous page. So let's see the proof. Let's prove item A. So let's just translate the statements, right? T is onto. What does that mean? That's the same thing as saying that for every B in W, T of X equals B has a solution, right? That's the definition. But now, because of the correspondence principle, by using the coordinate mapping, this is the same as saying for every coordinate vector of a B with respect to now, well, okay, I have to choose some bases, right? So there are these bases B and C sitting in the background. So let B, or let me just write it as B, let B be a basis of V and C a basis of W. And let's suppose this B has n elements. And let's suppose this C has m elements. Okay. So then the statement is true if and only if it's true for the coordinate vector. So for every B, if for every coordinate vector of that lies in Rm, which is just every vector in Rm, the equation, the matrix of T with respect to these bases times X coordinate vector equals coordinate vector of B in the output basis has a solution X, which lives in Rn. So originally the solution X was in V, and now the solution is in Rn. So any questions about that step? Could you ask just by speaking? Okay. So this is just the correspondence principle, right? And now this is a familiar thing. I recognize this. This is a statement about a matrix, right? The matrix being this matrix, right? And so this is the same thing as saying that the column space of this matrix is equal to Rm. But what does that imply about M and N? So this matrix T is an M by N matrix, right? So what does this imply about M and N?
Wouldn't this imply that n has to be greater than or equal to m because we couldn't increase the dimension, we can only decrease it?
Exactly. N is greater than or equal to M by something we did before the midterm, right? I won't repeat it. But then this is the same thing. So what is N? N is a number of basis elements of B, which is the dimension of V. And M is the dimension of W. So that's the proof. And part B is similar. I won't do it here. Okay. So all these theorems, you get them for free. These isomorphisms are a very powerful, useful thing. It allows you to import all the theorems also that you had in Rn to any finite dimensional vector spaces, which at a high level makes a lot of sense because, you know, isomorphisms preserve the structure of a vector space, preserve every linear algebra statement that holds. And so it's not surprising it would hold this as well. It would imply this as well.
Could you repeat why you know that N is greater than M?
This is because of a result before the midterm, right? That if you have an M by N matrix, then, I mean, another, okay, so another way of viewing this is to say that AX equals B is consistent for every B, right?
Right.
And for that to happen, the number of columns has to be at least the number of rows.
Makes sense. Thank you very much.
Yep. So this is from before midterm. Yeah. Any other question?
Professor, could you go back one slide?
Yes.
Thank you. Okay, perfect. Thank you so much.
Yep. Okay, so that's an example of a theorem translated. And another very important theorem that is translated in pretty much the same way is the rank nullity theorem. It says if T is a linear transformation from V to W, and both the dimensions are finite dimensional, but the dimensions are finite, then the dimension of the kernel of T plus the dimension of the range of T is equal to the dimension of V. The rank nullity theorem. And the proof will be very similar, right? What does it mean to be in the kernel of T, right? So a vector X is in the kernel of T. Sorry, just a second. Yeah. Okay. Sorry. So a vector X is in the kernel of T if and only if. Well, what does that mean? If only if T of X equals 0. That's a definition, but that's true if and only if. The same is true for the matrix of T and the coordinate vector of X. So this is in V, this is in Rn. Or I guess this would be in W, sorry, and this would be in Rm. But then this is just the same thing as saying the coordinate vector lies in the null space of this matrix. So that means that the dimension of the kernel of T is just equal to the dimension of the null space of this matrix. So again, in the background, you have some bases, right? B and C. The null space of this matrix with respect to B and C, which is equal to the number of free variables in the row echelon form of this matrix. And similarly, the same argument, the dimension of the range of T is the dimension of the column space of this matrix, which is the number of pivot variables. And so that's it, right? So the conclusion is that the sum of these plus the dimension of the range of V, range of T, is the total number of variables in this matrix. So this matrix is, what are the dimensions? Well, it's M by N, where M is the dimension of W and N is the dimension of V, right? So let's write that out carefully. And so this sum is equal to the dimension of V. That's it. So it's not hard. It's just, you just have to follow these isomorphisms. Okay, so any questions about that? Okay. So let me now get to change of coordinates, which is the most confusing topic in the course. And I'll start with an example just to try to make it less confusing. It's actually not very complicated. It's just very easy to get confused. It's very easy to get things backwards. Let's start with an example. Let's write down a vector x. Let's consider the vector 1 minus 2 in R2. So let's draw a picture of that vector. So maybe it looks, no, it doesn't look like that actually. Maybe it looks like this. Okay. And now that, now that we know about bases and coordinates, we actually know that what we've really been talking about the whole time is actually, x really is just its coordinates with respect to the standard basis. So let's call the standard basis E with the vectors E1 and E2 that we know and love at this point. And then, x is a linear combination, right? So it's 1 times E1 minus 2 times E2. And so really this vector is the coordinate vector of x with respect to E. So the picture is that, there's this, let's say, red basis E, which has my, two vectors looking like this. Okay, so that's a very familiar situation. Let me actually move this to make a little more space. Okay, now let's look at a less familiar situation, okay? Or maybe, so now let's consider a different basis of R2. Okay, so let's consider the basis. Let's draw it in blue. Let's consider the basis B with, let me just write the vectors. With the vectors 1, 1, 1, minus 1. Let's call these B1 and B2. So this is actually a very famous basis in quantum mechanics or in quantum computing. This is called the Hadamard basis. Now let's plot this basis. So here B1 kind of looks like this, and B2 looks like this. So it's a different basis of R2. But because it's a basis, I can represent X as a linear combination of these basis vectors. And I did this before using row reduction, and I got this linear combination. Yes.
Shouldn't B2 be x1, y -1? So shouldn't it be pointing down?
You are right. It should be pointing down. Thank you. I did it backwards. Thanks. B2 should look like this. Yeah. Okay. But certainly algebraically, the same x above is equal to minus half B1 plus 3 halves B2. Okay, you can check that. Okay. And what that means is that the coordinates of this x with respect to the B basis are minus half and 3 halves. Okay. So this is a different description of the same object, right? So the meaning of this is saying that if I wanted to, if I wanted to give the address for x in terms of the B basis, I would need to travel minus half in this direction and then 3 halves like this, and then I would get to the same x. It's a different description of the same vector. And, I have a way of translating between these two descriptions. Can anybody tell me how I would go from XE to XB? Well, I
Could you
mean,
just use
go ahead.
the m by n matrix of the transformation relative to E and the basis B?
Yeah, so it's kind of implicit in this setup, right? That how did I, what is this equation really saying? Well, it's saying that the coordinate vector of x in the E basis is equal to this matrix whose columns are B1 and B2 times its coordinate vector in the B basis. So, okay, minus half, 3/2. So in general, you have this relationship that x, the E coordinates, are just equal to a matrix, which I'm going to call P of E gets B times the coordinate in the B basis. Okay, where this matrix P of E gets B is just a matrix that has the basis vectors of B1 in its columns, right? So, I mean, in this case, okay, I might as well fill it out, right? This is just going to be the matrix 1, 1, 1, minus 1. Okay. And so if I wanted to translate between these, if I wanted to go from a B coordinates to E coordinates, I would multiply by the matrix P of E, PE gets B. Okay, which is just I'll just define, which is just the matrix that has these basis vectors as its columns. Okay, and how would I go back? Anybody see how to go back? If I just had if I had the standard basis coordinates for x, how would I get the B basis coordinates? Inverse, yeah, somebody said inverse, exactly. So I would just do P of E gets B inverse, which I'm going to call P of B gets E. Okay, so this is called a change of coordinates matrix. So definition, P of, so if you have two bases of a vector space, or of Rn, let's say generally, so if B and C are bases of Rn, then P of B, or sorry, I'll write it as C gets B. Is a matrix, is the change of coordinates matrix. And then the key property is it satisfies P of C gets B, X B equals, okay, I'll have to create some more space here. Maybe I'll just delete the word satisfies since this is not adding much. Sorry, this is the C coordinates. Okay, so this converts coordinates between B and C, and right now we've shown how to find the change of coordinates matrix when one of the bases is the standard basis. Okay, but now let's consider a slightly, let's add another basis to the mix. Let's add a C basis. So let's say the C basis has coordinates has basis vectors -1, 0 and -1, -1. C1 and C2. So let's plot it. So C1 looks like this, and C2 is going here. Okay, this is also a valid basis. And what again, I can write X as a linear combination of these elements, and I did it earlier, and I got that it's -3C1 plus 2C2. So that means that the coordinates of X with respect to C are -3, 2. And again, I have, I can translate from the C basis to the E basis by applying these change of coordinates matrices, P of, I guess, E get C, and this in this direction, P of C gets E. Right. So I have these three different setups. I have these three different bases, and I have ways of translating between C and the standard basis and between B and the standard basis. And those ways are not very complicated. I just stack the basis elements in a matrix. So in this case, it would just be -1, 0, -1, -1, which is C1 and C2. Okay, so the question, so any questions so far, by the way?
For the change of coordinates matrix, is that just, could we consider that as like a transformation, or is that just a normal matrix? Like,
yeah, it's a transformation, right? Because what am I doing with it? So it's a square matrix, right? And what I'm doing is I'm multiplying a coordinate vector. I'm applying it to a coordinate vector to get another coordinate vector. So it is a linear transformation from, in this case, R2 to R2.
Okay.
But it's actually a matrix.
Okay, yeah, that makes sense. Yeah, thanks.
So now the question I want to ask is, so let's think of these as languages, right? So sometimes this metaphor helps. So let's say the standard basis is English. And let's say the B basis is Bengali. And let's say the C basis is Chinese. Okay, so these are just three different languages for describing the same vector. It's actually not a bad metaphor. So I know how to translate from Bengali to English and vice versa. I know how to translate from Chinese to English and vice versa. How would I translate between Bengali and Chinese?
Could you translate Bengali to English, then translate the English to Chinese?
Exactly. Right. So concretely, the question is, what is the change of coordinates matrix between B and C? The answer is, well, okay, start with Bengali, then go to English, and then go to Chinese. Now, in mathematical terms, what does that mean, right? Well, it means you start with a vector in B coordinates, and to get it, to multiply it, to turn it into English, you have to multiply it by which change of coordinates matrix?
PE gets B inverse.
PB gets E inverse. So you just mean, I guess, E gets B, right? Okay.
Yeah.
And then now you'd get the coordinates in the E basis, and then now you'd multiply it by P of C gets E to get the C coordinates. Okay, so this seems like a good idea. Let's just check that it actually works. So let's check. Okay, so I guess this is one of those times when it really sucks that I have to create a new slide. Okay. Okay. Well. Okay. So let's. So in general, P of B gets C is just P of B gets. Oh no, sorry. C gets B. Right. I want to go from Bengali to Chinese. So this is why it's confusing. The direction of the arrows is confusing. As you can see, I still get confused by this. Just pay attention to the, think of this language metaphor, and it will help you make sure you got the directions of the arrows right. So you want to go from B to C. So to do that, first you go from B to E, and then you go from E to C. And now if you want to actually calculate that matrix, you use this fact that PC to E is just PE to C inverse times PE to B. And now we have written those down, right? So PE to B is the matrix that's written over here, right? This is, or sorry, B to E, right? This matrix is PB to E. So let's just, whoa, did I just clear that? Okay, what a drag. I guess I'll have to do that again. Okay, B, C, B to C. So yeah, all the confusion is because the arrows go from left to right, from right to left, which I guess if we were speaking Arabic, we would be happy, but okay. And now we've written these down. So PC to E is written over here. So it's this matrix, I guess -1, 0, -1, -1 inverse times this matrix with the Hadamard basis. That's 1, 1, 1, -1. And okay, I calculated the inverse of this earlier. It is, let's see. Yeah, it actually just happens to be this. And if you multiply these out, yeah, I'm not sure why I'm doing this. Okay, you get 0. And then here you get, I guess, -2. And then I guess here you get -1. And then here you get 1. And so if this is correct, then you should have that P, you should have that this is turning the B coordinates into the C coordinates. So let's check. So PC gets B times X B coordinates is 0, -2, -1, 1 times, so the B coordinates were -½ 3½ which is, so you get -3, and now you get on the bottom, you get ½ + 3/2 2, which indeed is the C coordinates. Okay, so it's not a complicated concept. Just be careful with the directions of the arrows. Okay. So to translate Bengali to Chinese, you translate Bengali to English and English to Chinese. So the general principle is just this. The change of coordinates matrix is a product of change of coordinate matrices to the standard basis. So any questions about this?
I have a quick question.
Yeah.
Does the change of coordinate matrix have to be square?
Yeah, it does have to be square. So that's a good question. Now, well, it has to be square because I talked about it being invertible. But the reason it's invertible, well, okay, in this example, I did this in Rn, but because every basis of Rn has n vectors, right? So if you make this P B to E matrix, it's going to have n columns, and each of them is going to be vector in Rn, so it's going to be square. And because they're a basis, it's going to be invertible. So these are always invertible, and they're always square.
So it's basically like the basis for B and C are square. So the change of coordinate matrix has to be square as well.
Yeah, that's right.
Okay, thanks.
Any other question about this?
Sorry, I might have missed this, but why did we do that step like where we inverted P C to E, or like couldn't we have just multiplied?
Oh, right. So well, the reason is that we wanted PE to C, but the thing that we wrote down was PC to E, right? And those two are related by inversion, right?
Oh, okay.
We wanted to go from English to Chinese, not from Chinese to English. So to do that, we have to invert the matrix.
I see. Okay, thank you.
Anything else?
Is there any particular reason why the arrows go from right to left instead of left to right?
Yes, there is a particular reason, which is that you multiply by vectors on the right. So if you look at this equation, right? So this actually feels very nice once you start multiplying by vectors, right? So the key property that these share, the key property that this has is that P C to B times X sub B, right? So now these B's line up equals X to the C. That's why the arrows go to the left. This is also why the order is opposite when you write function composition, because it's ultimately an artifact of the English language, right? That we, for some reason, we want to move from left to right, and we want to, plug in inputs on the right.
Professor?
Mm-hmm.
I have a question.
Yes.
Does this matrix have something to do with the matrix of T that are relative to B and C?
You're saying, does this have anything to do with the matrix of T relative to B and C?
Yeah, like the thing we did.
Okay, that's a great question. It does. Right now, there's no T in the picture, but I'll show you in a moment that it really does. So it's a great question.
Okay, thank you.
Oh, it didn't get erased. It just got moved. Weird. Anyway, let's erase this now. Okay, so now that was in Rn. So now I can ask the same question in V, right? Suppose I have a vector space V and I write a vector in two different bases. So given some vector space V of dimension n, well, and two bases, how do I relate and some vector x and v? There is a matrix P. Again, it's a matrix. It's an n-bind matrix. P. Let's do B to C. So again, such that B to C times the x coordinate vector, the B coordinate vector of any x equals the C coordinate vector for every x in V. Okay, so this is a generalization to abstract vector spaces. So maybe I'll just write more generally. And how do you find this? So there are actually two ways I'm going to describe to find this. So I'll give two proofs. One is related to the question that was just asked. So proof number one. So the picture is that I have V, and now I have two different isomorphisms to Rn. So one is I have P, so I have a B basis and a C basis, right, of V. So I have the P, I'm going to call it, let's see, what should I call it? So this is the standard basis of Rn. So I have the, let's see, how do I want to do this? Well, I won't give it a fancy new name. I'll just call it the coordinate mapping, right? We've been talking about this for a while. I have the B coordinate mapping, right? Which is an isomorphism between V and Rn. And then I have another coordinate mapping, which is the C coordinate mapping. Sorry, this is not, yeah. So I have two different isomorphisms between V and Rn, right? And now I'm asking, is there a way to go? So this contains a space. This is interpreted as a space of B coordinate vectors, B coordinates, and this is the vectors in here are C coordinates, right? So X lives up here. X sub B lives down here, and X sub C lives down here, right? So how would I get from X sub B to X sub C? Well, I could just, these are all isomorphisms, so I could just follow the arrows, right? So this has an inverse called PC, right? If I wanted to, and this has an inverse PB. So if I wanted to translate Bengali to Chinese in this case, what I could do instead is I could translate Bengali to abstract vectors, which is just like an object, and then translate that to Chinese, right? And so what I would get is that if I take P, C gets B. So I would take P, C gets B to be P, C inverse composed with PB. So the arrows that I'm traversing when I do this is I'm going up like this to V, and then I'm going down like this to PC. Okay, so and then this would be an isomorphism between B coordinates and C coordinates. And now let's just check that this has the desired properties. So this is the idea. And by the way, this is going to be a matrix, right? Because PB is a linear transformation from Rn to V. PC inverse is a linear transformation from V to Rn. So this is a linear transformation from Rn to Rn. Okay, so let's how do we find out what this matrix is? So this actually turns out to be very easy. You just use linearity. So to find the matrix, let's see what this does to the standard basis vectors, right? So what do I need? I need PC gets B applied to a standard basis vector of B. So I know that this equals the C coordinates of this basis vector, right? Okay, but what is the basis, what is the coordinate vector of B1 with respect to the basis B? Can anybody tell me?
Shouldn't it just be like 1, 0, and then as many zeros as there should
Exactly.
be? It should be like E1.
Exactly, because it's just 1, 0, 0, 0, 0, right? So this vector is just E1. So this is PC gets B, E1. But that's just the first column of C gets B, right? So this is an n by n matrix. So the first column is just the first basis vector of the input basis B written in the output basis C. Okay, but now what is the second column? So similarly, the second column is going to be what? By the same reasoning, what would the second column of this matrix be?
Is it just B2 in the B coordinate system?
Yeah, right. So this is equal to, you know, P, C gets B in the B basis, but you know, the whole point of this transformation is to change this to a C coordinate vector. So by definition, what you get is the C coordinate vector. And then if you repeat this, the conclusion is something very nice. So let me write the conclusion here. It's a red box since it's important. The conclusion is that this matrix, this change of basis matrix, is actually just you write down the basis vectors of the input basis, but you write their coordinates in the output basis. That's it. So it's ultimately not very complicated. And, you know, this is in particular, if the output basis is E, this is the matrix B goes to E that we've been writing in Rn before. This is a generalization of these matrices that were written here. B goes to E, or I guess PE gets B. If you plug in C is just the standard basis of Rn, then you get just that. So it's not really a new concept. It's just a generalization of the same old concept. So that's proof number one. Some people like proof number one. It's very concrete, right? You just check the columns of the matrix. And then, oh yeah, by the way, so I guess you have to check that this works for every X. But since it's a linear transformation and it worked on a basis, it's going to work for every X. Now let's do a second proof. Any questions about this?
So is the circle, is that the multiplication or the composition?
This circle is composition.
Okay.
Because these are not matrices, right? PB is not a matrix. PC inverse is not a matrix.
Okay.
But you can compose two things that are linear transformations to get something that's a linear transformation from Rn to Rn, which is a matrix. So I see what you're saying. I'm identifying linear transformations from Rn to Rn with matrices.
Okay.
So this is the matrix of. Yeah.
Does this only work if we have Rn and another Rn?
Yeah, I mean, so the point of this, I mean, it has to be n, right? Because both the bases have to have the same number of elements, right?
Yeah.
There's no way you could have an m here, right? These are both bases of V. And we proved that all bases have the same number of elements. So these both have to be n.
Oh yeah, okay.
Okay, so now, as somebody asked, there's a second proof which actually is even easier, but more abstract. So recall that we had this picture, right? You have V going to V, and you have a linear transformation. And now let's say you have these two bases, B and C. And now you have, these maps or whatever, both going to Rn. And now you have here the matrix, right? And we know from the correspondence principle that for every X in Rn, or in V, sorry, if you multiply this matrix times the coordinate vector of the input, you get the coordinate vector of the output. Right? We did that in the last lecture. Now there's a very slick thing you can do here to derive the theorem for free. And the idea is just take T to be the identity. Okay, so for T equals identity, so it does nothing. What does this equation say? Well, it says that the matrix of the identity with respect to this pair of bases times the coordinate vector of X in the input basis is equal to the coordinate vector of identity of X in the output basis, which is just the coordinate vector of X in the output basis. And that's what we wanted, right? So the change of coordinates matrix is equal to the matrix of the identity transformation with respect to these bases, which is just identity of B1, which is just B1 in the output basis, identity of B2, etc. Same theorem, different proof. Any questions about that? This is kind of, it's very slick, it's very abstract, but.
So are we just applying the transformation on the basis in X? Sorry, the basis, the B basis, and then that converts it to the C basis?
Yeah, I
Is that
mean, if you
what's happening?
follow what we review of the last lecture, right? How do you write a linear transformation as a basis? So, let me just write down what this matrix was, right? So we did this last time. This matrix was literally T of B1 in the C basis up to T of Bn in the C basis, right? That's just what a matrix of a linear transformation is.
Mhm.
And so what we did in this case is we did this slick thing where we took the identity transformation, which does nothing. And so we just got we got the change of coordinates matrix.
Okay, that makes sense. Yeah, thank you.
Any other questions? Okay, so those are all different ways of looking at change of coordinates. It's actually not very complicated. You just have to not get confused about the directions of the arrows. Okay. Any more questions about that? I mean, okay, I might as well not skip this step, right? So really the step was that this is identity of B1, identity of Bn, but then that's just equal to B1, Bn. Okay, so that's change of coordinates for vectors. What about change of coordinates for linear transformations, right? Well, let's again do it with an example. So let's say I have a linear transformation T from P1 to P1, polynomial degree at most 1, by just differentiating the polynomial. Okay. So now the point is, I could describe that in two different ways if I had two different bases for P1. So here's one basis, the standard basis of polynomials, right? And now the matrix of T with respect to this basis is okay. So it's follow the formula. It's d by dt of 1 in this basis. The coordinates in this basis and d by dt of t coordinates in this basis, which is, this is just 0 and that one is just 1. So that's the matrix of T relative to the E basis. But I could have another basis, right? There's no reason for me to have to use this basis. And this is actually a very, deep point that you can represent a linear transformation in different bases. And we're going to spend the next 2 weeks talking about it. Here's another basis, B, consisting of the polynomials 1 plus t and 2 minus t. That's a legit basis of P1. And now I can ask, well, what's the matrix of T relative to B as input and output basis? Well, again, it's going to be d by dt of 1, which is 0 in this. Sorry. It's not going to be d by dt of 0. That's exactly the point. It's going to be the derivative of the first basis vector. So d by dt of 1 plus t with the output written in the coordinates in the B basis. And then d by dt of 2 minus t with the coordinates written in the B basis. So what is that? Well, the derivative of 1 plus t is actually just 1. And the derivative of 2 minus t is just minus 1 in the B basis. And well, you can write this out. So 1 is actually equal to 1/3 times the first basis vector plus 1/3 times the second basis vector. And -1 would just be minus that, right? So I have two different descriptions of the same linear transformation. So different bases give you different matrices describing the same linear transformation.
Professor, can you explain how do you get 1/3 and negative 1/3?
Yes. So this 1/3, 1/3, this is the coordinate vector of 1 with respect to this basis, right? That's because 1 is equal to 1/3 times 1 plus t plus 1/3 plus, 1/3 times 2 minus t. Does that answer the question?
Okay, I see.
Right, because I have to write the first column should be the transformation applied to the first basis vector. So these are B1 and B2, let's say, right? So T of B1 is just the polynomial 1. And I need to express that again in the B basis. That's why I get 1/3, 1/3, because those are the coordinates. Does that answer the question?
Oh, yeah.
So different matrices describing the same transformation T. So before I proceed, any questions?
Yeah, in the first matrix, is the 1 supposed to be representative of a T, or is it supposed to be
Oh, that's a mistake. Sorry, it should be 1, 0. Because the derivative of T is 1, right? Not T. Thank you.
So is there a way to write like the 1/3, 1/3? Isn't there a way to like write it if it's the coordinate something? What you said?
Yeah, 1/3, 1/3 is the coordinate vector of the vector 1 with respect to the basis B. That's what this little red calculation means.
Can you like write it down with like the box thing? I don't know how to say this.
Sure. Yeah. So the box thing is saying that 1 comma B. So what this means is that if you take the matrix, or it's not the matrix. So 1
combination.
Right. So 1 comma B is 1/3 1/3. That's what this is saying. Is that what you wanted me to write?
Yeah. Thank you.
Yeah. So that's what's going on in this matrix here. And the second column, I didn't even have to do the calculation, right? Why? Why did I know it would have to be -1/3, -1/3?
It's the opposite of T.
It's the opposite of the first column.
Sorry, yeah.
Right, but that's right. And the point is that the coordinate mapping is a linear transformation. So coordinate mapping of -1 is negative the coordinate mapping of 1. Okay. So the point okay, so this is just an example. Now the question I want to ask is, how are these matrices related? And the sort of beautiful theorem or fact is that the matrix of T in the B basis is the matrix of T in the E basis. But now, again, thinking of these as languages, if I wanted, if I had the input written in Bengali, but then I wanted to apply the transformation, but the transformation only knew English, what would I do? Well, I would translate it, right? I would translate it to English, do the transformation, and then translate it back to Bengali. Okay, so this actually works beautifully. This is not additionally confusing given the previous stuff about change of coordinates. If you understand change of coordinates, at least the statement of this should be very intuitive. The proof you can just check. You know, you can, well, I won't belabor the proof. The proof you just check both sides, right? So the proof, you just check that the thing on the right satisfies the key property that's needed. So what does this need to equal? Well, this needs to equal T of X in the B basis. And you can just check, again, you just check it on the basis vectors and it just falls out. Okay, so there's nothing new involved in the proof of this, but this is very important. And the point I want to emphasize here is that these are two different descriptions of the same transformation, right? Which one do you think is better? Which one do you think is simpler? Which one would you rather do computations with?
E.
E, right? Why?
Because it's a bunch of zeros and ones.
It's a bunch of zeros, yeah. So the point I want to highlight is there are many different transformations, but some bases yield a much simpler matrix than others, right? So E is better than B. E gives a simpler matrix than B. And so the question, which we'll now study for the next 2 weeks, is given a linear transformation, which basis gives the simplest matrix? And this is a very deep question, so in some sense, this is the end of the kind of language development, like vocabulary building portion of the course, where we basically learned a lot of definitions and we learned some connections, but by and large, the connections themselves were not very surprising, even though they were quite beautiful. In the next section of the course, when we answer this question, we're really going to discover something surprising that is totally, as far as I could tell, I was very surprised when I learned about this. And this is part of the reason for the power of linear algebra. So that's chapter 5 starting next week. But that's it for today. So any questions?
Yeah, I just wanted to be sure on the notation. Like for example, like the theorem that you wrote on the bottom left. So with that notation, we are reading from right to left. Is that right? So like B to E, E to E, and then E to B.
Yeah. The reason we're reading from right to left is I'm imagining what's going to happen when I multiply this by a vector, right, on the right. So first I'm going to, this all comes back to the fact that if you do A times B times X, that's actually first you multiply by B, then by A, right?
So we would multiply first by P, E gets B, and then okay.
I mean, you could do it in any order because matrix multiplication is associative. But the reason I'm reading it from right to left is that conceptually, that's what makes the most sense, right? I'm starting with the vector on the right, and I'm transforming it one after another to get the vector on the left.
Right. Okay. Thank you.
So both of those matrices that we found, if we multiplied a vector by them, we'd get the same result, like the one based on E and the one based on B?
No, absolutely not, right? They're different matrices. So the one based on E satisfies the following property, right? The property that this satisfies is that if you give this an input vector in E coordinates, it outputs the output in E coordinates, right? That's what that matrix means. The matrix on the right has a completely different meaning. The meaning of this matrix is if you give it a vector, input vector in B coordinates. So if you give it the B coordinates of an input vector, then it gives you the output vector in B coordinates, right? But if you give the second matrix a vector in E coordinates, it's going to output some garbage. Does that make sense? It's like if I had some kind of, I mean, it's like if I started speaking Bengali to somebody who only knows English, right? The result will not be the same. Does that answer the question?
Yeah, it answers the question. I guess I just have to absorb it a little.
Yeah. So this is it's a difficult concept if you're not used to this, because I'm saying that these are both describing the same thing, but they're describing it with respect to different frames of reference. That's the way to think about it, right? So these are different descriptions these are descriptions of the same object, but with different frames of reference. So basis is like a frame of reference. And what you're asking is, are the descriptions literally the same, right? That's what you meant when you said, are the matrices, if you multiply the matrices by a vector, do you get the same answer? The answer is no.
Okay.
Because the matrices are literally different, right? As you can see here.
Okay. I get what you're saying. Thank you.
Yep.
Wait, so does each T have like infinite number of ways of describing? Yeah. Okay.
Yeah.
Okay, cool.
Professor.
Mm-hmm.
I just have a question. When you said it was associative, it's different from what order is, right?
Yeah. Associative is this property that, associative means that A times B times C is the same as A times B times C.
Okay, where you put the parentheses, basically.
Yeah. So that's really, so commutative means the order doesn't matter, and matrix multiplication is not commutative. It's very important, but it is associative.
So, Professor?
Mm-hmm.
Oh, sorry. Okay. So for this page, I'm a bit confused. For B, the matrix we got in the end would be so do we write B in a way in a column, or do we write it in a row? Because the matrix in the end, if we want to get one and a negative one, then we multiply we multiply them by so I think we multiply them by B1 with 1 on 3 first, and B2 with negative 1 on 3. Is that the matrix saying?
No. So you have to look at the columns, right? So this first column here, this is the coordinate vector of the polynomial 1 with respect to the basis that's given here, right? And what they're saying is you do 1/3 B1 plus 1/3 B2 is equal to 1. Does that answer the question?
So
so you see B1 and B2, right? 1 plus T and 2 minus T.
Yeah.
If you take 1/3 times B1 plus 1/3 times B2, you actually get 1, because that's 1/3 plus 2/3. The T's cancel.
So do we multiply them by B, and we put B in the front, and then we multiply by the matrix?
No, you don't put B in front, right? So this subscript B means it's a coordinate vector. It's not a multiplication. So you don't ever multiply by B.
Oh. Okay.
I mean, you can't multiply by B here because B is also not a matrix, right? B is just a basis.
Yeah.
So maybe focus on what's written in this red box here. So, the first step is I need to express the transformation of B1 in the B basis, right? So that's d by dt of 1 plus t. I need to write its coordinates in the B basis. So I calculate it. It's the polynomial 1. And then in the red box, I realize that the coordinates of 1 in the B basis are 1/3, 1/3. And that's why there's 1/3, 1/3 in the column.
Okay.
Yep.
Thank you.
Sorry, but can you elaborate? Bottom left corner theorem, you said that the order doesn't matter, but I thought matrix order.
Oh, sorry. Yeah, so I should have been clearer about that. The order matters a lot, but the order in which, okay, so the question was, why do you multiply from the right? Why am I, when I read these expressions, why do I always read them off from the right, right? And I explained that that's because, when I apply this to a vector, the vector is going to appear on the right. And then I'm going to think of, first multiplying by the rightmost matrix, then the second rightmost matrix, et cetera, right? So all I meant by that comment was that I could actually multiply these two matrices together first. That's not going to change the answer.
Oh, I see. Okay.
You can definitely not swap the order of the matrices. That's a no in general in the course. Unless they have some special property, you cannot do that.
That makes sense. Thank you so much.
Wait, sorry, could you repeat that last part you said?
I was just saying that matrix multiplication is associative, which is this property here. So this is equal to this, right? That doesn't affect anything, which is equal to AB times CX, right? You can put parentheses wherever you want.
Okay.
But however, this, as we have been drilling into, this is not true, right?
Right.
Yeah. So by order, I just meant the order of putting the parentheses.
Okay. Yeah. Thanks.
Yeah.
That makes sense.
Okay. Well, I actually have to run, but yeah, thanks. So that's it.
Thanks, Professor.